Interesting, I haven't really been having latency problems anymore. Good morning, everyone. Hope everybody's doing well this morning. I moved the mic up here because, you know, I'm a bit of a handsy talker. So hopefully that reduces the number of mic hits we have. I saw last time people were keeping track of the number of times I hit my mic, which is, you know, well within your rights. But I didn't realize I was doing it quite so often as that. So, yeah. Good morning, everyone. Hopefully everything's going well in your worlds. It's not quite 9:30, I guess, but, you know, whatevs. So, let's take a look. Let's get our, tutorial links. That's cool. Yep. Let's get our lecture slides opened up for today. Some person last time thought that the lecture slides were, that we weren't going to have any actual material covered this week. No such luck, I'm afraid. No such luck. It's kind of ominous and looming. That's okay. You can hear me fine with this up here, I hope? Let me check my sound. Let's see how it goes. Yeah, that's fine. Cool. All right. Doop. No, I don't want it in browser. Jeez. No, not... Criminally. Alright, there we go. Ba-dam! You know, a professional prof would have had this set up ahead of time, but, you know. Unfortunately, you've got me to deal with. Cool. Nope, there are no tutorials this week. You have hoped correctly. No, tutorials will start next week. How does the naming conventions of the lectures work? What exactly is W21? That's winter of 2021. Yeah. Just, it's to distinguish this semester's lectures from last semester's lectures. Basically, that's it. Okay, so, we're gonna get into, the lecture material very shortly. Before we do, I just have a quick sort of, CS stands for computer science. I just have one other quick thing that I need to make you guys aware of for this semester, sort of in the realm of things that I should have covered when we were talking in the syllabus, but, you know. So, and it's towards the end of the semester, it is going to be a probable outcome that I may have to take a few days and not do lectures because I will be indisposed. Not quite sure when exactly that's going to happen, but that's happening because right now my wife is in her third trimester of a pregnancy for a human child, and you know, it's kind of the way these things go that you don't know quite when that's gonna, you know, happen, but the expected date of delivery is around April 12th, I believe, which sort of puts it definitely at end of the semester territory. But when that starts to happen, I will need a couple of days off. The TAs are going to be covering the lectures, though, so I'm telling you this now so that you guys aren't alarmed. Oh no, where's the prof gone? He must have fallen down the stairs or something. So yeah, oh, thank you guys. Aw. But yeah, so just so you're aware of that, that's going to happen at some point. It's definitely not up to me. So, what are we naming the kid? Well, he's a boy, but we haven't really chosen a name yet because we we have this thing when we... this is going to sound strange, but we have this thing when we named the cats. We had, like, some idea of what the name could be, but we wanted to wait until we met the cat, until we actually named the cat. So I think the same policy is going to apply to humans. Well, I mean, it's important, right? It's important that you specify. No, I'm not. We're not naming the kid ComSci1MD3. Yeah. So anyway, that's a thing. Thank you all for your hearty congratulations. John? Yeah, maybe. For a while we thought Felix, but, we'll see. Anyway, we should do some actual work today. Instead of all of this goofing off, talking about the future. Jeez. Okay, so, lecture topic 1 on programming. This is going to be your sort of first bite out of the apple that is programming. So, I guess I'll sort of start off by talking about what programming is. So this is a very interesting class for me because, like, normally I've got at least a few comp sci guys thrown into the mix. This semester I checked the listing of students on Avenue or on Mosaic, and we've got two comp sci guys in this whole class. Which, hello comp sci guys. But yeah, it's like which faculties are you guys from? Just shout out in the chat. I imagine there's quite a few of you from science. Normally I get a pretty good representation from the business faculty as well. Normally a few health sci guys thrown in there, but I sort of mentioned this during the life sci. There you go. I mentioned this during the talk on the syllabus, but essentially the correct way to think about this class is as a math class, right? So all of you guys who are super into all of the mathy type stuff, you've found the right class. Lots of life sci guys. Science, life science, math and stats. Yay! Humanities. Cool. Welcome to Math World, from Math World to you people who study humans. I don't know. Math is a lot more clean, in my opinion, than humans. But that's and I imagine I'm gonna find that out at the end of this semester, right? But yeah, commerce, life sci, math and stats. I'm not sure what P and B is. Let me try to figure that out. P and B. X-ray tech. Ooh. Yeah. So, astro. Oh, come on. Astrophysicists. Now that's a discipline. So programming. What is program? Yeah, math gang. Imagine not having numbers to represent yourself. Math gang. So what is programming? We have computers. Computers are these really interesting objects because I don't know about you guys, but like especially lately, I have been spending an ungodly amount of time staring at a computer screen. It's like there's this XKCD cartoon about like modern life. It's like this guy's staring at a computer screen and he's like, man, I need these pixels to be in particular patterns of color on this screen, and if they're not in the right patterns of color, then, that has implications and consequences. And it's like, well, you could also say the same thing about writing on a piece of paper. But essentially, like, computers to a lot of people are these sort of mysterious objects. A lot of people sort of, like, I sometimes refer to cell phones as magic rectangles, because a lot of people seem to treat them like they're magic rectangles. But I'm kind of here to tell you guys that computers are actually very simple. They're very complicated in one sense and very simple in another. A computer, all it does is a few simple things very, very quickly, right? And these things that it does are they process instructions, right? We're not really going to get into assembly programming, but when you take all of the stuff that is happening on computers, on a computer system that you can see right now, pretty much everything boils down to a few hundred what are called assembly instructions, which are the actual instructions that are executed by your central processing unit. So when we are programming in a programming language like Python, every statement in Python creates a certain number of these CPU instructions that are executed by the CPU when you execute the program. Structurally speaking, a program is a series of instructions. This is, well, it really depends on the programming language, but right now we are talking about imperative programming. Imperative meaning to give instruction. So, if you think about like the Harry Potter books, one of the 3 unforgivable curses was the Imperious curse, which is to make someone follow your instructions, which is what we do with the computer, essentially. Except the computer doesn't have a conscience or a sort of moral standing, I guess. So it's perfectly okay for us to order computers around because they don't have souls, essentially. So anyway, when you write a program, what you are doing is you are composing a sequence of instructions that are going to be executed by the computer extremely rapidly. Ordinarily in such a small fraction of a second that it is practically instantaneous from a human perspective. So, so that's essentially what a program is. Let me just check to see if I haven't lost everybody already. Yeah, we made smart rocks and taught them math. Yes, exactly. Precisely. Well, it's interesting, right? Because, like, I imagine computers would be a lot less popular if they weren't made from one of the most abundant substances on the planet, which is silicon, right? Anyway, so in order to write a program, we have to formulate a problem, right? We have to know what the program we want to write is before we write it. Preferably. This is why it's important to have specifications. So, question. What is the square root of 25? I'm sure all of you know that. Question. What is the square root of y? The square root of a number y is x such that x times x is equal to y. We can write a program to find that. This is actually a problem that we will be solving later on in the course. We require some basics before we get into it. Here's another problem. Let's imagine we have a function, f, monotonically increasing on some interval from a to b, such that f at a is less than 0 and f at b is greater than 0, or equal to in both cases. So you have a function that kind of looks like this, right? Monotonically increasing on some interval from a to b, and at some point there is an intersection with the x-axis. So the problem, the programming problem here, is how do you determine what the x-intersection is? It's normally reasonably easy to find the y-intercept for a function of this type. But what about the x-intersection, right? Can we write a function to estimate it? Absolutely. And let's find the x-intercept within some precision epsilon. This guy kind of throws a lot of people off. So what we mean when we say precision is we want to find the x-intersection within a window around, like, when we find what we think is the x-intercept, we want the actual x-intersection to be within a certain confidence interval around that, hypothetical, this calculated x-intercept. It's okay for the x-intercept we calculate to be slightly off from the actual one, so long as it's off by less than epsilon. That's what epsilon means. So, here is an algorithm. So long as b minus a is greater than epsilon, do steps 2 to 4. Step 2, calculate the midpoint. Calculate this midpoint here. It's a plus b divided by 2. Cool. If the function at the midpoint is less than 0, it's sort of below here, then we know that the x-intercept is going to have to be in the interval from m to b. So we take the bound a and we set it to m, or we set m to it, so that we then recalculate, we do the same approximation again with the new reduced bound from m to b, right? We rename m as a for the next iteration. Conversely, if m is above the this x is, the x-axis, then we have the exact opposite position, and the position that is illustrated in this diagram. In this case, if m is above the x-axis, we know that the intersection must be somewhere between a and m. So we iterate the process once again. We take the currently calculated m to be b for the next run through of this algorithm, and by this process, if we keep running this process, you can see that this process reduces the size of the interval by a factor of 2 each time the algorithm executes, right? This means that eventually, for however small epsilon is, eventually the size of the interval is going to be smaller than epsilon, right? Once the size of the interval is smaller than epsilon, we know that it doesn't matter where we consider the x-axis to be, the actual x-axis is going to be less than epsilon units of whatever away from the any point within that interval. Therefore, we have found the solution. And you can make epsilon reasonably small so that you can get a fairly tight view on that. But because of the limits of computation, you can only do that so much. You can only make it so small, as we will see when we talk about topic 6 or so. Let me check to see if I haven't lost everyone yet. They don't have souls yet. That's true. So, there's another XKCD cartoon about them doing something in Python and just importing soul. But yes, anyway. So let's talk about programming languages. Am I framed well? I'm a little low. Boop. There we go. I got a separate webcam that's got a light built into it, so that I can move my laptop screen without you guys being, getting motion sickness. Maybe just get it out of frame. There we go. Is the epsilon given? Yes. In a problem formulation like this, the epsilon would be given. Do you only have to show up to one of the tutorials? Well, I mean, you have to show up to one of the tutorials per week, and you actually showing up to the tutorials is not recorded in any manner. We're not giving participation marks or anything. It's sort of primarily for your own benefit that you engage with the tutorials. However, I would recommend engaging with the tutorials. In particular, one of the focuses for next week's tutorial will be getting all of the requisite software operational. So, you know, probably a useful thing to show up. Also, I think you guys are going to be doing the number game, which is always a classic programming example. Bonus marks for watching Monty Python and the Holy Grail. I wish, but no. So, with programming languages in general get class, like there are a bunch of different classes of them. There are different types of programming languages. One of the more important distinctions is whether your programming language is declarative or imperative. Python is an imperative language. As I already stated, imperative languages are best thought of as instruction-based languages. Declarative languages they're more like I write down a mathematical equation and the computer will figure out how to calculate it itself. They tend to be higher level languages. That's another distinction that we'll get into a little bit later. When a computer scientist says high level and low level, those have very specific meanings. So imperative languages, such as Python, tell you how the result is obtained by giving a sequence of instructions. Imperative languages more directly relate to the actual machine code instructions that are executing on your actual physical CPU. Each step is simple enough that it can be followed. So for the case, in the case of the x-intersect, restrictions on the input are imposed. F is monotonic. Additional input is needed. You need the upper lower bound and epsilon, and the result is only approximate with epsilon. There is repetition. So when we are talking about imperative languages, we're talking about conditional statements. We're talking about looping statements. We're formulating things as do this, do this, do this, do this, go back up here, do that, do this, do this, do this, jump down here, do that, do that, do that, etc., etc. You are controlling what the instructions are and the flow of the executions. When we talk about things like conditional statements and looping statements, these are generally speaking called control flow, because we are controlling the flow of the program. This is distinct from a declarative language. We're not going to be studying declarative languages in this class. The two guys who took or are taking 1JC3 will know all about these, because Haskell is a extremely declarative language. So one of the huge advantages of declarative languages is that you can express quite a large number of CPU instructions in a small number of lines of code. The sort of touchstone that I'm going to be using for a lot of this is Haskell. Personally, I've done quite a bit of programming in Haskell. It's a beautiful language. However, it's the sort of language that you really should know some other programming languages before you get to it. It looks a lot more like the type of mathematical computation that you would do by hand. Everything, like in Haskell, you don't even get loops, you get tail recursion. But, you know, again, we're not covering it explicitly. But I will be referring to it a few times. So, yeah. Oh, geez. Whoops. There we go. Try that. Boop. Oh my gosh. No. Stay there. Okay. There we go. All right. Cool. So, yeah. Declarative versus imperative. we're going to be doing imperative. So, algorithms. An algorithm specifies a sequence of instructions to be executed by a machine that, when provided with input, will eventually stop and produce some output. So, this is a very important formulation. 3 primary components of an algorithm. A set of instructions, whether you're encoding those declaratively or imperatively, doesn't matter. You have a sequence of instructions. You have an input, or actually, most functions will have several inputs. You have a set of inputs, and you produce some output. Input, output, instructions in the middle. This is how all computers operate. Very fundamental. Here are some examples that are not computers. A cookbook recipe is an algorithm to be executed by a human in order to cook food, right? When you are cooking food, your inputs are the ingredients that you are cooking with. The instructions are the recipe instructions, like mix dry ingredients, then mix in wet ingredients, let sit to rise for 3 hours, then, put in oven at X temperature for Y amount of time. And then the output for this algorithm is some kind of comestible foodstuffs. Another example would be traffic lights. So sometimes, most of the time, traffic lights only take the time as an input to calculate what the electrical signals to the light bulbs should be. Other times, there are car presence sensors, which are also taken into account. The instructions, you can imagine with traffic lights, there's a set of instructions in there that relates what time it is to what the state of the light bulbs should be. And that would be the program. So, yeah. Let's see what people are thinking. Say it louder for the people at the back. Yeah. Yeah, I'm just a loud, handsy talker, and you're just going to have to get used to it. Yeah, if you want to take notes, that's entirely up to you. I'm not going to tell you how to be a student. I'm just going to tell you about programs. So, algorithms. Further on the subject of algorithms. The computation prescribed by an algorithm goes through a sequence of states, starting from an initial state and leading to some eventual end state. The idea of state is also pretty important inside of the context of computing. You can think of the inputs that are being provided to your program as being the initial state. You can think of the output that is produced by your program as being the resultant or end state. And there are going to be a number of intermediate states. The intermediate states in a program are the values that are maintained in memory as your program is executing. We shall see this once we do an example. If you want to see what the intermediate states inside of your program are, that's called performing a trace. Tracing your program. It's often extremely useful if you're trying to figure out what the problem is with your program to look at the intermediate states, to look at the memory as the program is executing. That's if you're trying to fix a problem in a program, that's actually the first place that you should be looking. Well, actually, no, I'm sorry. It's the second place you should be looking. The first place you should be looking is the actual produced output to see what it looks like, how much it's off by. You can often glean some very interesting information from what the actual output is. But sooner or later, you're going to have to take a look. You're going to have to peel the lid off of this can of sardines, take a look inside, and see which ones are bad and which ones are good. And the only way to do that, really, is to trace your program. It's basically pretty much all practical debugging tools are ways of organizing program traces to make it easier to trace programs. So the term algorithm comes from the 9th century Persian mathematician, and I'm can't really pronounce it, but I think it's something like Al-Khwarizmi, something like that. This guy, who is pictured on this postage stamp, published an arithmetic treatise on calculating certain values, the Latin translation of which became Algoritmi de Numero Indorum, or Algoritmi on the Numbers of the Indians. So, because India was basically everything east of Constantinople in those days. So, yeah, it's interesting. Man, those medieval Islamic scholars, they were just knocking it out of the park. We also derived the term algebra from a very similar mechanism. Algebra is actually a guy's name. Or, a Latin bastardization of some guy's name. So, what is an algorithm then? Let's discuss what they are mechanically. So, an algorithm, when we're talking, and we're now talking more about computer algorithms, a computer algorithm is supposed to be executed mechanically. That is to say, it's like you're building a machine. You have a crank at one end, and you have gears in the middle, and, you get ice cream out of the other side or something. And what you don't want in a mechanical system is for some guy to have to put his hand in to move one of the parts manually, right? The more automatic the machine is, the better the machine is, generally speaking. This is true for mechanical machines, and it is also true for algorithms. You can think of an algorithm as a mathematical machine. An algorithm should be precise. So each instruction and the next possible instruction must be unambiguous. So when you're writing an essay, what you write in your next sentence has some connection to the previous sentence, but there's also an element of creativity that enters into it, right? It's kind of up to you what you write your essay about, or the manner in which you write your essay. It requires a human being. What you want to do, the way that you want to design an algorithm is such that there's absolutely no creativity required in order for the algorithm to execute. It might require creativity to design an algorithm, but it should require absolutely no creativity whatsoever to execute it. Every statement must proceed from the next completely unambiguously. At all points in the algorithm, what the computer does next must always be deterministic, because that's the way the computers work. Oh, maybe I'm hammering it a little too hard. The other thing about algorithms is that they need to be effective. So each instruction must be executable by the underlying machine. This is not really going to be much of a problem for the types of problems that we're going to be presenting you, guys. However, historically speaking, within the context of computer science, and particularly, I would say, artificial intelligence, this has been a bit of a sticking point, this guy. If you go back into science fiction that was written in the 40s and the 50s and the 60s, you'll notice that one of the interesting little hiccups that prevented the science fiction of the golden age of science fiction from being faithfully implemented by the scientists who were trying to do so was the problem of essentially computer perception. It turns out that having a computer or a robot, for example, understand what a human is saying, that's not something... Like, that's a description of a problem that is extremely difficult for a computer to actually execute, because it's not generally well understood how human beings understand things, let alone how we would design artifice to understand things, right? So that's an example of a thing that you might have, like, a high-level description for how an algorithm might go about doing it, but whether or not you can actually translate that into machine code, that's an entirely different story. So yeah. Let's see. Have we lost it? Should my son's name be Algebra? I don't know. Maybe. Yes. I agree. Somebody's asking about the test already. Will we ever be tested on theory-based questions? Generally speaking, no. Generally speaking, you will be tested on your ability to program. Headset. Is that... Shouldn't be. This one isn't even connected. So, if it were retractable, I would retract it. Because I got this really nice one. Yes, cool. So, here's a question. With this algorithm for calculating the x-intercept that we went over in such great detail, what would happen if the function at the midpoint was 0 after instruction 2? So, the formulation here, what do you guys think? If the function at the midpoint itself ended up equaling 0 exactly, is it true that the algorithm is not precise because it is ambiguous? Is it true that the algorithm is precise, unambiguous, but the inputs which lead to the function at the midpoint being 0 are not permitted? Or either instruction 3 or 4 is executed, it doesn't matter. What do you guys think? I'll leave this up for a moment. I'll tell you right now, it's a bit of a trick question. So we got a few people saying number 1, a few people saying number 2. One guy thinks it'll be... thinks it'll be the last one. Okay. Opinion is divided, let's say. So, question. Is this algorithm ambiguous? So, in one sense, yes. In another sense, no. It is ambiguous in the sense that we have a branching condition here, and the conditions overlap, right? You do this if f at m is greater than or equal to 0, and you do this if f at m is, less than or equal to, and you do this if f at m is greater than or equal to. Both of these cases contain equal to as a case, right? So which one of them do you choose? So that could be a potential source of ambiguity. However, if you're assuming that this is an imperative language, the fact that these instructions occur in a numerical sequence actually removes that ambiguity. If this were actual programming code, you'd hit this statement. If f at m was equal to 0, you would execute this, and then you would move on. You wouldn't actually get to this case. So, because we're talking about an imperative language here, it is unambiguous. So, what the? I'm getting one of those presidential alerts or something.
Stay-at-home order.
Oh, okay. All right, folks. Just received official word from the government via my cell phone. We're all ordered to stay at home. If you were already at home, good job. But if you're not at home, you need to go home because Rob Ford said so. Yeah. If you're not in Ontario, then I guess you can go out for a pizza. But if you're in Ontario, yeah, don't worry, it's not. Yeah, I don't know about you guys, but whenever I get one of those, because it says presidential alert, even when it's something like an Amber Alert, and don't get me wrong, Amber Alerts are really serious, but I always feel like it's like our notification of incoming nuclear holocaust or something, you know? It sounds like an air raid signal, you know? But, oh, did I say? Doug, Rob, whatever. Whichever, Mr. Ford. Sorry. Whatever. Sir, you haven't seen the sun in weeks. Well, it is wintertime, but yeah, I totally get it. We are still allowed to go for walk and exercise around. If you're not at home, it's treason. It's treason, then! Yes. Oh my god. Yeah. Sorry, guys. What a boomer mistake. Yeah. Yeah. Well, anyway. Oh. Yeah, everybody makes jokes about the purge until the purge actually starts happening. Oof. I want to keep... Okay. That's enough. I have to keep the stream apolitical, or else YouTube will throw me off of YouTube. So what's the... Yes, let's get back to the question. So, the answer to this question is kind of none of these. This one's definitely not the case. Because it's an imperative language, you will execute one of these or the other of these. You know, it's if this, do this, otherwise do that, right? So, you know, that makes them exclusive. So this one, number 3, is out. The only way this is true is if we add a step where if f at m is equal to 0, then we understand that we have actually found the x-intercept, so we can stop the algorithm because we have found the x-intercept. But we would have to add something to this algorithm in order to do that. So there you go. Question: is the output of this algorithm always unique? I will add to that question, is it always unique for unique inputs? Because if the algorithm is unambiguous, then it should produce the same output for the same input every time. That's actually, excuse me, that's a fundamental law of computation, or it should be. If your algorithm does not produce the same output for the same input every time, something is fundamentally wrong with it. So much so that you will not pass test cases on assignments for doing such things. So, I'll just give you the answer for this one. Is the output of the algorithm always unique? For unique inputs? Well, no, because you could, in theory, construct, two functions with the same x-intersect, but different functions, and they would have the same output with different inputs, so no. There you go. So, here are some fundamental questions about algorithms. What do we mean by correctness, and what do we mean by efficiency? Correctness is actually a reasonably easy thing to define with respect to algorithms. Is the output that we got the one that we intended or expected? Right? So, in this particular, like in the x-intersect algorithms case, we can do the calculation by hand. We can use other mathematical means to verify what the x-intersect should be for a particular function, right? You know, if it's a quadratic, then you use quadratic formula to solve for the x-intersects. So if our algorithm produces the output that was expected or intended, it is correct, and if it did not, then it is incorrect. Efficiency is a little more difficult to nail down because there are a few different ways you can measure efficiency. Efficiency, like you can talk about whether it's time efficient, instruction efficient, what about the worst case scenario, what about the best case scenario, what about on average? Is it memory efficient? There are a bunch of different parameters that can characterize the execution of an algorithm, and you can determine whether or not you're in a desirable range for each of those. Generally speaking, the ones that we're most concerned about are time and memory. And as you'll see later on in this course, those two things are actually sort of inextricably linked to each other. Which, you know, should make intuitive sense. The more memory a program uses, the more time it takes to execute that, you know, amount of memory. So, here's another question. Can we compute the exact x-intersect by taking epsilon equal to 0? What do you guys think? Can you have a non-deterministic algorithm or a pseudo-random algorithm? Well, that's actually an interesting question. Definitely possible. Like, pseudo-randomness is definitely a thing. In computers, we can't generate true random numbers because everything is deterministic. Basically, what happens is you run a function on a seed number, which is usually like the system time in milliseconds or something like that, something that changes frequently, such that it scrambles it enough to be it to look or be effectively random, but it's not actual true randomness, right? Yeah. So even algorithms that have pseudo-randomness are technically still deterministic. So yeah. No. Everybody seems to think, no. You cannot. That's true. While that works hypothetically in mathematics, you know, if you were able to execute these, if you were able to iterate this algorithm an infinite number of times, you could, in theory, achieve this result. However, because computers are physical systems that are bounded by the limitations of this veil of tears, you can't actually achieve an algorithm that runs forever because it will take forever for it to run. And you will be long dead by the time it never finishes. But yeah. Also, if A and B are rational and the x-intersect is irrational, it will never be reached. So there's also like a technical reason related to the way in which numbers are represented that we'll get into when we do floating point numbers. So yeah, this is a whole nother topic, and I'm not, given that we have like a minute and a half left in class, I think we'll leave it for next week. But we're going to start to talk about conditionals and loops and that sort of thing. Actually, I'm not sure we get to loops. Do we get to loops? Yeah, we get to loops. Okay. Yeah, so that's, I think I'm going to call it here. I'll answer any questions you guys have. Yeah, there we go. Haley knows what Haley is talking about. Can I explain the epsilon thing? Yep, no assignments this week. You're welcome. And the epsilon thing. Yeah, I can explain epsilon again. So epsilon is the size of the interval in which the x-intercept is known to exist when the algorithm terminates. The question essentially is, can we compute the exact x-intercept by saying the interval around the interval in which we know epsilon to exist is 0. The size of it is 0. We compress it down to a point, right? That sort of thing often works in physics, but it doesn't work in computers, right? Computers are, again, physical objects that are limited by physical restraints, like the amount of memory they have available. That's the other thing. Imagine this, right? It takes memory to represent decimal places, right? Roughly speaking, this isn't quite true, but roughly speaking, if it takes more and more memory the smaller the number is, right? Because you have to, like if you were doing it in scientific notation, you would require more and more memory to represent the exponent, right? The exponent would get larger and larger and larger, like -10, -100, -1,000, -10,000. That would get longer and longer and longer as you tried to make it narrower and narrower and narrower and narrower. And eventually you would run out of system memory to be able to represent the size of that exponent, right? Even though, functionally speaking, there's really not much use for anything beyond, times 10 to the -15, because at that point you're talking about like electron charges and numbers like that. Despite that, it's actually quite possible to do very, very, very small numbers in computers. But there's kind of and it's kind of like a thing that an engineer would think about, but it's like, at a certain point, does it really matter that you've calculated it to that level of exactitude? Probably not, Again, this is the sort of thing that people who are concerned with doing things physically in physical reality, that's the sort of thing they're concerned about. It's in theory land, everything works out and everything is happiness and sunshine, but yeah. Could you not program the computer to execute some mathematical way of solving the exact x-intercept using standard mathematical strategies? Yeah, absolutely. But, we're sort of talking about this strategy, right? Definitely you can get the computer to do, like quadratic formula or something. You can even, if any of you have used MATLAB, MATLAB has a symbolic math toolbox so that you can get MATLAB to do your algebra for you. And I'm pretty sure Wolfram Alpha does the same thing, but... Why is the output b minus a less than or equal to epsilon? So, when you achieve the output, the interval should be, like, the size of the interval should be smaller than epsilon. If the size of the interval is smaller than epsilon, then you know the midpoint of that interval, the actual x-intercept must be at least as close as the size of the interval to the midpoint of that. Well, actually, technically, it is at most as close as half the size of the interval to the the midpoint of that interval. So, if the interval is smaller, if half of the interval is smaller than the epsilon, then you've guaranteed that the x-intercept is within epsilon. So, hopefully that's a decent explanation. Yeah. Cool. Well, I imagine you guys have to run along to class. I'll probably log in for office hours if anybody wants to drop by, but I don't expect people will have much to talk about just yet. Do we do any coding during lectures or like examples of Booleans and stuff? Yes, we will do some programming in class for sure. It's the purpose of the tutorials is to do guided programming exercises. In lecture, we're going to be doing like probably 3 or 4 parts theory to 1 part demonstration. But, you know, at the moment, we're really just going over like the introductory level basics stuff. So there hasn't been a whole lot to actually program yet. I suppose I could have done this one, but you can always request me to do a programming example, by the way. Will this class involve any linear algebra? Yeah, probably a bit. Nothing, like, we're not going to get you to do eigenvectors or anything like that, but certainly the representation of matrices as 2-dimensional data structures in computing, that's definitely a thing that we're going to be talking about. Vectors as lists or tuples, you know. Like, a lot of the structures that you use in linear algebra will pop up in this class again, particularly once we get to data structures. But we're not going to be doing a lot of stuff like... well, I say that, but I did also put, you know, calculate the determinant of a matrix recursively on the exam last semester, so... Yeah, I'm gonna assume that you know at least some... Okay. I will assume that you either know a little bit of linear algebra or you can figure it out from a description and a... Like, I'll describe it. I'm not just gonna say, like, okay, calculate a determinant and not describe to you what the determinant is. Do you need to buy the textbook? No. None of the problems that I'm going to be assigning to you are out of the textbook. They're all in the Jupyter thing, so you don't need the textbook to get at the questions from this. In fact, the textbook that's assigned doesn't even have practice problems in it. It's just if you like reading, basically. Like, it's a really good textbook, and it's really valuable to read it, but no, it's not like, I'm not going to be asking questions out of it or anything like that. Okay, if you guys have any further questions, you can join me in my office hours. But, yeah. Take her easy, folks. See you all on Monday.